Hi, in this video, we are going to cover four things. What Kafka actually is, explained in a way you can repeat to your team without everyone quitting. Why our digital bank needs Kafka, especially for bill payments and settlement. How Kafka topics let services communicate without annoying each other. And finally, how partitions and consumer groups give us speed and scalability without praying to the server gods. So let's get started. What is Kafka? You can Google the official definition, but let me explain it in plain English. Kafka is basically a big central pipeline. Services don't call each other directly, instead, they send messages into Kafka. One service shouts, "Hey, payment processed." Another one goes, "Let me update the ledger." So instead of services blowing up each other's phones with direct calls, they just drop messages into Kafka and whoever cares listens. Officially speaking, Kafka is distributed. It runs across multiple servers. It's durable. Messages are written to disk and not stored in memory. It's scalable. You throw millions of events at it, and Kafka says, "Nice try." And it's replayable. You can reread old events. Now, why do we need Kafka in our bank? In our payment architecture, multiple services are involved: payment orchestrator, bill pay worker, settlement service, account service, biller service. If we connect all of them with REST, and if one is slow, everything slows. If one is down, everything breaks. Retries becomes a nightmare. Kafka fixes this by letting services communicate asynchronously. Orchestrator publishes bill pay requested. Bill pay worker processes and emits bill batch ready. And settlement service consumes bill batch ready. And no tight coupling, no blocking, no screaming. So, for our digital bank, Kafka gives us decoupling, which means services don't need to know each other directly. We get asynchronous processing, we get resilience. If a consumer is down, events are still stored in Kafka. Scalability, we can add more consumers to process events faster. And replayability, we can reprocess events if needed for recovery and debugging. Next, let's talk about Kafka topics. Think of a topic like a folder or channel where all related events of one type are stored. Producers write messages into a topic, consumers read messages from that topic. In Kafka, each event in our business flow is represented as a message. So when we say event or message, we mean the same thing. It's simply data being published to or consumed from a topic. So let's walk through the Kafka topics we will use in our bill payment system and who interacts with them. Bill pay dot requested. This is where the new bill payment starts its life. The payment orchestrator publishes to this topic and bill pay worker consumes it to start the processing. Bill pay enqueued. Once the worker has placed the payment into the batch, it publishes it to billpay.enqueued. The orchestrator consumes it and updates the payment status to batched. Bill batch ready. When the batch is either full or hits its cutoff time, the worker publishes bill batch ready. Settlement service consumes that and prepares the external submission. Bill batch submitted. After settlement service sends the batch externally, it publishes bill batch submitted, and the orchestrator consumes it to mark the payment as submitted. And finally, we have bill pay.status. Settlement gets the result, success or failure. It publishes bill pay.status, and the orchestrator consumes this and moves the payment to either posted or failed. Every topic has a job. Every service knows what to publish and what to consume, and the communication stays clean, decoupled, and async. Now, let's talk about Kafka partitions. A topic in Kafka isn't one long list of messages. Think of it as a road split in two lanes. So partition 0 can be lane 1, partition 1 can be lane 2, and there can be many more partitions and many more lanes like this. Inside each lane, messages stay in order. Across different lanes, order doesn't matter, just like real traffic. So, why does Kafka do this? Because partitions let Kafka process workloads in parallel. If lane 1 is processed by consumer 1 and lane 2 by consumer 2, we are not waiting for one lane to finish before the next one can start. That's why Kafka scales horizontally instead of choking under load. Now let's connect this to consumer groups. A consumer group is basically a team of consumers sharing work. Kafka automatically assigns partitions to consumers, like consumer A is reading partition 0, consumer B is reading partition 1. So no duplication, no fighting, no confusion. Just clean, distributed load balancing. And here's the big insight. The producer never decides who gets the message. It just writes to a topic. And Kafka routes partition to consumers in the group. Now let's take this into our payments world. If we use payment ID as the key, Kafka sends all events for that payment to the same partition, which means ordering is preserved where it matters. But if our traffic spikes, we just spin up more consumers and Kafka scales out automatically. So the final takeaway is partitions give us parallelism and ordering, while consumer groups give us scalability and fault tolerance. That's why Kafka doesn't break, it scales. In the next video, we will move from theory to hands on. I'll show you how to run Kafka locally on your machine using Docker Compose along with Kafka UI so you can actually see the events flowing. See you all in the next video. Thank you.